Welcome to Session 3. My name is Arnold and I will be your instructor. In this session, we will talk about the prediction pipeline. In order to be used in a forecast, your data has got to go through several stages. In the first stage, you do preparation, which includes things like normalizing the values or adding missing values. You could also have noise removal or the addition of synthetic inputs. In the second stage, that data is windowed as we've described in Session 2. We also perform something called feature engineering, which we will discuss towards the end of the session. In the final stage, you will use that data to train your model and also to run some kind of prediction. The training stage is where you define your model and where risk minimization occurs. Finally, the trained model is used to perform predictions. You will find that the preparation stage is something that you want to fix from the start and not change too much. You will have to make quite a few changes to your training stage. This involves the model definition and the kind of structures you would want to use in your neural networks. Most of all, you would do many changes in the feature engineering stage. To summarize, you'd fix your prep stage early and make most of the changes in feature engineering or windowing, and of course the model itself. In AutoCAF, we have separated the stages into different files. The prep stage is handled by prep.m, and this contains all your pre-processing code. Next, the windowing stage is handled by a file called pre.m. This controls windowing as well as feature engineering. The train stage is controlled by two files. The network.m file defines your network, while config.m contains all the configurations for your network. We'll discuss this later on in the session. Predictions are controlled by something called config.eval.m, which you don't really change very much. And finally, the whole is orchestrated by a file called main.m. Once you click main.m, you'll see these buttons appear in the output window on the right. The prep button corresponds to running the script prep.m. Data corresponds to the windowing stage. Train and status correspond to the network side of training your model. Because training is asynchronous, you need to repeatedly check that all your configurations have been completed using status. In this example, I've got 60 configurations that should be run, and of these, 50 have been completed, 8 are queued, and 2 are being trained. Why do we need multiple configurations? Well, the reason is because we often want to try many different settings at once. And sometimes we also want to repeat the same setting again and again. All of these configurations are stored in one place, config.m. This is a simple config.m file. And what you will notice is that each of these lines is in the format value, definition, name. You can ignore all the text in purple. Those are comments and are just meant for your own understanding of what these configurations actually mean. Anything in purple is not actually run by the AutoCAF system. One other thing to notice is that spaces are very important in AutoCAF because we use a language called Smojo to make the definitions. In Smojo, spaces are significant. Here we see there are actually 4 names being defined, and these 4 names are all of them used in network.m. So in other words, all of the configurations that you define in config.m will ultimately be used in your network.m. NN size might mean the size of the network, for example. Input size could mean the size of the input vector window. Iters could mean the maximum number of iterations you want to run the network for. And solver type could mean the kind of solver you'd use in training. Of course, the actual meaning of these different names would depend on how they're used in network.m, as we'll see shortly. All these names defined here have just one value on the left, which means that there is exactly one configuration that is run, one in which NN size is 8, input size is 2, iters is 1000, and the solver type is Atom. Here's an example where we change the definition for NN size so that it can take on one of 3 values, 18, 16, or 32. Again, the spaces are important. The double brackets simply means a list of multiple values, and each value represents one configuration. We've got 3 values for NN size, Just one value for input size, one value for ITERs, and two values for the solver type. So all in all, we have 3 times 1 times 1 times 2, which is 6 configurations to run. Now you can also repeat each of these 6 configurations using the command repeats. So 10 repeats simply means running these 6 configurations each 10 times. We have therefore 60 configurations in all to run. All configs which you define will be trained and tested separately. They have nothing to do with each other. Before you can extract and analyze the results of training, you have to wait for all your configs to complete before viewing their results. Always start with sensible defaults. We've discussed this previously with your network configuration. You want to use config.m to scan a few parameters with repeats, like 5 repeat for example. Once your optimal parameters are fixed, you want to use more repeats, 10 or 50 or 100, to confirm the results to get a best-in-class model. You would oftentimes have to run more repeats with an SGD solver because it gives you a more variable result compared to Adam. The next thing to do is to check the loss graphs. I will show you how to make sense of loss graphs shortly. Clicking on this button will give you the loss graphs. Each pair of lines shows you one configuration. So in this case, the red lines all represent the test losses from your various configurations, while the blue lines represent training configurations. Here you can see some of the training has stopped abruptly, and this really is a sign of early stopping. It simply means that the test losses have started to increase. Along with the loss graphs, you should see a table at the bottom, and these give you more details about the losses for each configuration. You can click to sort based on test loss. Only the test loss is displayed because this is the most important metric to consider when evaluating a model. Lower test losses are better. Once you sort by test loss, the top configuration is the best one, and you can read off the values of the various names you defined in config.m. So in this case, the best configuration was one in which the neural network size was 8 with an SGD solver. In summary, the prediction pipeline has 3 separate stages: preparation, windowing, and training. In forecasting, you oftentimes want to make use of multiple configurations. Firstly, to understand if the model is giving the right answer consistently. Secondly, to extract the best model in its class. And thirdly, for you to be able to scan multiple parameters to extract the best one. Next, you want to look at loss graphs. These graphs are the most important graphs that you will need in creating neural networks for forecasting. They are the primary diagnostic for you to troubleshoot your networks, and they can tell you a lot about what to do if you're not getting the results that you expect. As a first step, always establish a baseline risk before you start work. This baseline could be, for example, persistence, or if there is an existing industry baseline, you could use that. Because persistence is very competitive for short lead times, you should always include that as one of your benchmarks. Let's say you've trained your models and you get a graph. You want to check that the training loss is smaller than the test loss. On the graph on the left, you can see that the training loss is larger than the test loss. Well, the first thing you want to do is to check your data and your network. One possible bug is that the test data is contained within your trained data. It could also be that the test data is very short. If, on the other hand, the results look too good, and by too good I mean that the train and test losses are very close to each other, then you want to again check for overlapping test and train data sets. Once you're done with these basic checks, there are 3 other scenarios that your training could fall into. In the first case, both test and training losses remain high. What this means is that the network is simply unable to learn. The first thing you need to check is if your network is too small. Expand it. The other thing you want to do is to check that the data you feed your network is normalized. Unnormalized data, especially large values, will lead to a network which is unable to learn. In the second scenario, the test loss stays high while the network trains well. This simply means that the network is memorizing the training data without actually generalizing to the test data. A network like this is not very much use. You want to check if the network is too big, in which case you can shrink it down. You still want to check for normalized data. Data which is not normalized can actually lead to memorization. You also want to understand if the data is too noisy. A very noisy data can lead to a large gap between the training and test losses. Lastly, you have to ask yourself if the data is actually predictive. Data which is not predictive will not give you good test results. You can fix this by changing the test data or perhaps creating new features which are more predictive. Lastly, you want to also look at regularization. Regularization can take two forms: dropouts, which we'll discuss in the next session, and also a weight regularization, which we'll also discuss in the next session. This scenario is probably the most likely one that you'll find yourself in. You will have to use all of these techniques in order to fix this problem. In the third scenario, there might be some gap between the training and test losses. This means that the network is learning but can improve. You want to try increasing the features or fine-tune your existing features, or perhaps check if the gap is again due to noise. In the final scenario, your training and test losses look very good. In this case, you need to check for reproducibility. The way you do this is to rerun the training at least 100 times to see if there's any variation in the results. You also want to check next the forecast lag to see if this is okay. Finally, you want to work on the features to try and reduce lag. Next, we want to see how to do windowing in AutoCAD. Windowing is the second stage after prep, and in windowing we do two things, both the windowing and the feature engineering, where we will need to make many changes. The file that controls this again is pre.m. We will always want to separate out our training and test data into train.csv and test.csv. These are both inputs into pre.m. And the outputs are called train preprocessed and test preprocessed respectively. The input data is not windowed. It's data where each line represents a single snapshot in time. And once windowed, we would have an input vector with the actuals. So let's say we have a train.csv. Time increases in this file from top to bottom. So the top numbers represent data earlier in time, and the numbers further down the file represent data later on in time. The resulting train preprocessed.csv is just a row of numbers, and each row represents a window. And this transformation is facilitated by the pre.m file. Selectors are a simple way for us to select and transform data from the train or the test CSV into the preprocessed versions. Let's look at a simple transformation in pre.m. The function to use is transform, and in here there are two selectors which correspond to two parts in the preprocessed files. A:5 simply selects the t+5 value from the original train CSV. A represents the first column. A0 to -1, on the other hand, selects t+0 to t-1, again from column A, from train.csv. The first of these, A5, is oftentimes the actual y, and the second part, which is the A0 to A-1, would be our input window. All in all, we have selected three values from the old file, train.csv, to put into the new file, train preprocessed.csv. Because it is the first selection, A5 represents column 1 in the output file, and A0 to A-1 represent columns 2 and 3 in the train preprocessed file. So t+5, t+0, and t-1 are put into the train preprocessed CSV in that order. If we have again train.csv, and time is increasing from top to bottom, and this is our pre.m, this would be t-1, this would be t+0, and that would be t+5. These are selected and put into the first row of train preprocessed.csv. The first column is t5, because we've selected A colon 5. And the second and third columns would be T0 and T minus 1 because we've made the selection A0 to A minus 1. We do this for the next row and for the next, and so on. As an example, suppose we have a single data set, in other words, one column in your train or test CSVs. If you have a data window of 18 months, the red dot represents T0, and the T plus 1 AT is the Y that you want to forecast for. This is how you would write pre.m. The label would be A180, in other words, selecting 180 days into the future, while the data window would be from A0 to A minus 540, which is 541 columns in your input vector. A180 selects T1 plus AT from column A of train CSV as the first column in train preprocessed.csv, while the second selector selects the values T0 to T minus 450 from column A again, but this time as columns 2 to 542 in train preprocessed CSV. All in all, train preprocessed.csv would have 542 columns. This windowing is done again and again and again and again until the end of the file is reached, and stops when the Y value T plus 180 corresponds with the last row in the data file. So in your train preprocessed.csv, oftentimes you want to make the first few columns represent the actuals that you're trying to forecast for, and subsequent columns represent the input data into your network. Next, I'd like to explain to you a bit about feature engineering. The first thing you have to understand about neural networks is that they are actually quite bad at any kind of general computation. They are instead very good at learning and recognizing regularities in your data through hierarchical clustering. And this is true for most ML techniques. Let me explain what this means. Let's say you have a picture, a face. How do you know it's a face? And that's because it consists of eyes, a mouth, and a nose. And these features, eyes, mouth, and nose, themselves are composed of subfeatures, lips or teeth, etc. Some key ideas. Neural networks are great at hierarchical clustering, and this means that they are robust against noise or missing features. An image could miss a mouth or a nose or a single eye, and you would still recognize it as a face because the other features are present. So the learning is successful when it can be reduced to clustering. Otherwise, neural networks will not be able to solve a problem. Here is a hard problem for a neural network. Most of us would have no problem guessing the last value. But because this can't be reduced to a hierarchical clustering task, it is actually very hard for the network to forecast the next value without any help from us. This is where feature engineering comes in. There is oftentimes little or no clustering that can be done within windowed data unless it's very repetitious like what we see here. The problem is that if you have a spiky signal in time and you have the first window, well, that's the input vector into the network. We have the next window further on in time. We have a different input. What we see clearly is that the responses might be about the same, but the vectors are quite different. So what we need to do is to transform these input windows so that they result in vectors which are close together and therefore can be clustered. So again, the problem with having just raw windows is that similar situations are mapped to vectors that are quite far from each other. This means that we need more clusters to learn a task, and therefore increasing the chance of memorizing. Feature engineering is simply a way for us to convert the raw window into a collection of features, and this could help further in clustering. How this works is that we transform data within that window into a set of features. For example, in this case, I've used the maximum, the minimum, and the mean, but you want to use many other features. We do the same for the next window. And what we find is that the x's are about the same, and therefore clustering works better. A feature is simply any function from Rn to R. It could be the maximum, the minimum, the mean, squares of difference, the runs, etc. This is really where domain knowledge, intuition, and a lot of practice come into play. You'd first always start with a raw window and then refine that using features and testing your neural networks to see what works. This is how you might do it using the pre.m. We are trying to forecast t plus 10, windows from t0 to t minus 10, and we convert this window into three features. A10 represents the y, what we're trying to forecast for, and the next three numbers together are the input vector into the network. We've come to the end of session 3. I'd like you to revisit lab 1 and to create a prediction for SGTEMS. Be sure to try and troubleshoot your graphs using the guidelines I've given you. Good luck.